before I forget. There we go. Yeah, so do either of you have any just general questions about 1047 before we begin? And I'm sorry, TJ, I did not see you come in. I had my my participation list was cut off, so I thought it was just Andrew and I in here, but it's so great to see you as well. Andrew, how about you? Do you have any general questions you want to ask? You'll notice that 1047 D2L is set up exactly like 1046, so it's not going to be any surprises that way. And TJ saying, no worries, I don't have much this week. Fantastic. And you'll both notice that D2L is set up very, very similar to Math 1046, except there isn't that crazy refresher unit, so you don't have to worry about passing in a placement assessment for this one. We're just going head first into matrices. And I did have a slide here that I wanted to show you. So where we're leaving off from last unit in 1046 is the last unit we looked at systems of linear equations in two variables. So if you have two linear equations with two variables, so x and y, that equation can be graphed, will graph a line. So this 3x minus y equals 7 is one line, and then 2x plus 3y equals 1 is another line. And the two equations are called a system of equation, and the point where they intersect is the solution to both equations. So when x is equal to 2 and y is equal to -1, that's going to solve both of these equations. So that's what we did in Math 1046. Now we talked about the difference between systems of linear equations being inconsistent and consistent. And the idea of inconsistent is that there are no solutions because you have two parallel lines, and because they don't intersect, there isn't a solution. And then we talked about a system that's consistent, and in a consistent system you are going to have solutions. Either you're going to have just one because there's only one intersection point, or you're going to have many solutions because the two lines overlap. So that's kind of the review of where we left off with the linear equations. What we're moving into is the idea of using matrices as a tool to solve systems of linear equations, but this time instead of having two variables, we're looking at three variables. So with three variables, we have x, whoops, get back my pen here, we have, there we go, let's see, there we go. We have variable x, variable y, and variable z, and instead of these equations graphing a line, now they're graphing a plane. So we're looking at this sort of in 3 dimensions. And when you're solving systems of equations in 3 variables, we're looking for a solution where all 3 planes come together. And then you'll get a solution for x, for y, and for z. That's going to work with all 3 of these solutions. And a matrix is the tool we use to solve that x, y, and z. So is there any questions around that idea of moving from an intersection of 2 lines to the idea of an intersection of 3 planes, because we're dealing with variables in like 3 variables? Andrew, how does that look? Have you gotten that far yet in matrices? Awesome. And feel free, Andrew, to grab your mic too. I think TJ doesn't have a microphone. That's why he goes to chat. So I always look back to see. But you can do whatever is more comfortable. TJ, how about you? Are you on the right thing too with that? Are we on the same page? that pre-type. That's awesome. So, oh, sorry. So in terms of set rules, do you mean in how we solve a matrix? So the idea of, from here, instead of using addition, substitution, elimination, what we're going to use is a matrix. So I'm going to wait for TJ to set that up. But what I would want to do is take these three equations and turn them into a matrix. So what I'm going to do is take the first equation and I'm going to set it up in columns where my x values line up, where my y values all line up, my z values line up, and my constants line up. So for this first equation, I have the coefficient of 2 in front of the x, so that becomes that. The coefficient in front of y is missing, so it's 1, and the coefficient in front of z is 2, and then my constant is 18. So that's the first row in this matrix. And then TJ, you're saying about the rules. Are there set rules, like how you can multiply the first line by -5 and then add it to the third line? I was just wondering if I can be wrong on doing things like that. Am I going to read more into it? No, you've got it. There, when you're doing matrices and you're trying to get it into that row echelon form. So for instance, if I just finish this quickly, -1, 1, -1, 2, and 9 represents that second equation, and 1, +2, -1, and 6. And you notice that I've kept my signs of the coefficients. That's really important in my matrices. What I'm trying to do next is using, through row operations, I'm going to try and reduce this into row echelon form. And that row echelon form is where you have ones across the diagonal, and then like that. And then you'll have x, y, and z here. So how you get to this form is by doing those row operations. Are there rules that are involved with that? There are some. The biggest one to remember is the order in which you get the rows into this echelon form. That's the biggest one, and I find that if you do it in the right order, then you will have better luck at getting the answer. So TJ, did you know that there was an order to this? I'm going to bring up a whiteboard just so I have more room. So let me just quickly write that one down again. So this is the matrix that I got from that systems of equations. So what I want to do is go from that matrix to this one, where I have ones down the diagonal and zeros under all of my ones. So that's right, TJ. So there is a set rule in terms of order. And if you follow the order, then what will happen is that you won't mess up what you already did. What you might find is you're trying to get this into this diagonal of ones with zeros underneath them. As you go through, if you don't do it in the right order, then you might get this set as 1, and this set is 0, and this set is 0, but trying to get this 0, this is going to go back, this is going to change. So if you do it in the right order, then you have less opportunity to mess up what you already did, because there's nothing worse than having to go back and redo something that you've already done. So the set order is this. I'm just going to choose a different color here. You want to do that position first, then you're going to do the 0 underneath that, and then after that, oh, I've had a brain fart, I have to look at my notes. and then the 0 underneath that, and then you're going to do this position, this one, and then this one last. And that's called Gaussian elimination, is when you're getting the ones in diagonal and then the zeros underneath it. Now, that's the first sort of stage of 9.1. And the reason why you get it into this stage is that we said that this is for value x, y, and z. If you get the matrices into this form, then, let me grab another thing, whatever, let's say that we get our constants to look something like this. What this means is that looking at this very last row here, that's telling us that we have 0x plus 0y plus 1z is equal to 6. And if I were to simplify this, I'm actually figure out that z is equal to 6. And now that I know that z is equal to 6, just based on that final row, I can then go to my second row and solve for y based on z. Now I don't have it all filled in, so it's a bit of a jump to see that, but that's what we're trying to work towards. So as you're trying to transform your matrix from this form to this form, if you do the positions in order of 1, 2, 3, 4, 5, and 6, you'll have better luck and not have to go behind. But in your textbook, if you look in chapter 9.1, I'm just looking for the page number, they do list like 3 rules to look at. And I'm going to find that page number for you. Page 709, if you want to write that down, it says the following row operations produce matrices that represent systems with the same solution set. Oh, wait, is that the? Yes. So there's matrix row operation rules on page 709, and those rules are basically what sort of matrix row operations you can use. So one of them is that rows can be interchanged. So you can, for instance, if you, this first one here, if I start with this matrice, what I'm going to do is, get my pen, I'm going to start with position 1, which is this 2, and I want to make that 2 a 1, because that's what should be in that position. It should be a 1. So one of the easiest things I can do is, remember this is row 1, row 2, and row 3. I can just switch row 1 for row 2. And great, TJ. Yep, so that's exactly what you're looking for. So on page 709, it gives you these rules, and the rules are that you can first of all, is that any rows can be interchanged. So that would be my first step for this, would just be to interchange row 1 and row 2. So I'm going to put row 1 at the top, and I'll put row 2 at the top, and then I'm going to move row 1 down and keep row 3 the same. So interchanging rows is okay, and you can see right there that I've already that just by exchanging those rows, I now have 1 in my first position. And then my next thing that I need to do is look at position 2, which is this 2, which has to be a 0 now. So I want to change this to a 0, and then I have to think of a row operation that will work with that. So the second rule that they state in the textbook is that any element in any row can be multiplied by a non-zero number. So basically you can multiply anything in a row as long as it's not 0. It would make it really easy if you could multiply a row by 0 so that you could get your zeros in position, but you can't do that. So that's not allowed. And the third one states that that you can add rows together. So that's just seeing if there's anything else. Nope. So that's really the three rules. You can switch rows. You can multiply rows with a number that's not a zero. That's including multiplying by fractions. If you multiply by a fraction, that's the same as division. So you can multiply, divide rows, and you can add or subtract rows together. Those are kind of the three things that you're limited by, but really those three things will enable you to get to that row echelon form, that reduced form. And you'll find that you'll start getting good at knowing what you need to do to get it to that point. For instance, whenever you need to have a 1 in position, you can always multiply by the reciprocal. So, for instance, if you have, let's say you have the number 5 in a position that needs to be a number 1, you can multiply everything in that row by 1/5, because 1/5 times 5, the 5's cancel out and you're set with 1. So anytime you're trying to get 1, you can just multiply by the reciprocal, and that will cancel out the number and you'll get 1. So you'll see it with practice that you're kind of using the same row operations pretty much each time. The other thing to not be worried about is if you start to get fractions. Fractions are going to be solutions, and that's okay. Just take a deep breath. If you get a fraction, you can still work with that as well. So I could go on and we could solve this, but TJ, you said you've brought questions, so I'd like to get to those before we do anything along these lines. Andrew, how does this sound so far to you?
So far, so good. I was kind of having some questions along the lines of TJ's, like strategies for what operations to use. But I mean, by the sounds of it, it's just kind of, at least in the beginning, it's trial and error until you get a better grasp of it.
Yeah, you're exactly right. And really this idea of making sure that you do it in the proper order is going to be big for you. Make sure that you don't mess up this order and try and do the far one here before you do the other ones in front, or you're just going to have to redo work. And really, the only three things you're going to be doing is interchanging rows. You're either going to be multiplying a row and then adding it to another row, or you're going to be multiplying by a fraction like I had here so that you can get it back to 1. There really isn't much more. Actually, there's nothing after that. It's those three strategies that are going to help you to rearrange the matrices to get it into that form. And it sounds like we're all on the same page too, that both of you are at the same spot, so that's great. TJ, do you have questions that you want to post up on the whiteboard? I can clear it and then give you some space. So I found out the other day, if you go into MyMathLab and you highlight text and then hit Control Copy or Control C, you can then go right into the whiteboard and Control Paste it. So or Control V, which is pasting, which is really kind of cool. So you got the first one done, good TJ, and you think you know what you're doing with the second one. Cool. Section 9.1 is really just getting to know a matrix, how it's set up given your equations, and then putting into this using Gaussian elimination to get it into this form, and then at the end they bring it further and show you that you can keep on going and get zeros in these positions, and that's called Gauss-Jordan elimination. And then you don't have to do any back substitution, because once you get zeros in these three places, you're then going to get your answer for each of the variables. Oh, 9.2. Yeah, 9.2 is actually quite short. What they're looking at in 9.2, and I'm just going to bring up that PowerPoint again, and it'd be good just as a just as an introduction. So I'm just going to bring back my PowerPoint. Here we go. So I was just showing in this slide the difference between Gaussian elimination, which is, oops, I didn't have my, maybe go back. There we go. So in this slide, I'm just comparing Gaussian elimination, which is this one here, where you have the ones on the diagonal and the zeros underneath, but above the ones we don't have zeros. So this is Gaussian elimination, where you figure out just one of the variables and then you back substitute to figure out the rest. With Gauss-Jordan elimination, you get the ones across the diagonal, you get zeros below, and then you keep on going. And when you keep on going, there is a sequence. So just as I said before that you're going to do this one first, then this second, this position third, fourth, fifth, and sixth, the next sequence, just so that you have it, is going to be position 1, position 2, whoops, and then, doesn't like me writing so small, position 3. So I'll arrow that. So just make a mental note that this 0 here is the next one that you're going to do, and then this 0 here is the fourth position, and then this 0 is the last 0 that you complete to get it into Gauss-Jordan elimination form. And what's so cool about Gauss-Jordan elimination, it takes time. It takes about 3 pages of work to get to this form. It solves all of your variables for you. You don't have to do back substitution. So this would be your z variable, this would be your x variable, x is equal to -2, and then, your y variable, and then your x variable is equal to 3. So that's kind of the beauty of Gauss-Jordan elimination, is that once you get a matrix into this form, it solves itself. But what I wanted to show you is about 9.2. So 9.2 is talking about a system of equation in 3 variables and the difference between inconsistent and consistent systems. So if you think back to when we're talking about linear equations that graph lines, if we had an inconsistent system of linear equations, it was 2 lines that were parallel. And because they were parallel, they didn't intersect, so they didn't have a common solution. So in a system of equations in 2 variables, it would give no solution because the lines didn't intersect. We're going to take that same concept to a system in 3 variables, and instead of picturing lines, you have to picture planes. So that's what these 3 graphics are showing you. So if you have a system that is inconsistent in 3 variables, it can mean that 1, the planes just don't intersect at all. So that's what's showing here. So you don't have an intersection point. Or it could be that you have 1 plane that intersects the other 2 planes, but not all the planes intersect at 1 point. And the same thing here. So you have 2 that intersect and another 2 that intersect, but at no point do all 3 intersect in the same place. So if you have 3 equations and they don't all intersect at the same spot, then that's going to be an inconsistent system, and there aren't going to be any solutions to that. And in a moment, I'm going to show you what a matrix would look like, what a matrix looks like when you don't have any solutions. So I'm going to show you that in a moment. But first, it's just important to understand what it looks like not to have any solutions. And then just like in systems of linear equations, we also have consistent systems, and consistent systems will have a solution. Either you have one unique solution, which is similar to two lines that intersect in one spot, or you have a dependent system with infinite solutions. And what that means is that, well, in linear equations, it means that you have two lines that are on top of each other. In a system of three variables, you're going to have where they intersect along a line. So all three planes kind of intersect along this line, and any solution along this line are going to be a solution for all three equations. Or maybe the three planes, whoops, maybe the three planes line up. So this last one here, whoop, there we go. This last one is where you have all three planes on top of each other, and therefore it's going to be all the solutions for all of those planes. So it's important to understand the difference between having no solutions for a system of equations in three variables and also having one or infinite solutions. When you look at a matrix, and you're trying to find out how many solutions there are, the first thing you're going to look for is this diagonal row of ones. And you can see here at the bottom, we're missing a 1 here, and we have all zeros, and then our constant is a 6. That's going to tell us, be the sign that we are dealing with three equations where they don't all match up at one place. So we have no solution. So if you ever get a matrix where you have a row of all zeros equaling to something other than 0, then that's going to be a no solution. So that's an example of a matrix that is showing an inconsistent system. We know that consistent systems that have one solution are always going to look like this, where you have ones diagonal, and you can then figure out what each of the variables are. So this is your regular system here. That's going to give you one solution. But the infinitely many, you can see that we again have the zeros on the bottom, but this time our constant is also equal to 0. So this is an example of a matrix that has infinite many solutions. So either you're going to get one where you have all zeros but your constant is not equal to 0. You're going to have just your normal system set up, or you're going to have a system where again it's all zeros but your constant is also equal to 0. So that's infinitely many systems. Or you're going to have a non-square matrix. And a non-square matrix is where you have two rows but you have three variables. So your variables and your rows don't match up. So you can see here that I have three variables, x, y, and z, and I should have three rows, row 1, row 2, whoops, and row 3, but because I don't have row 3, that means I have a non-square system, and non-square systems always have this infinitely many solutions. So that's just something to keep in mind if you get a non-square system. So that's what 9.2 is about. It's about identifying a given matrix, and just by looking at the matrix, understanding whether you have one solution, no solution, or infinitely many. So if I were to make a study sheet, I would have these examples of matrices, and they're in the textbook as well. I'd have an example of a matrix, and then beside it I would say whether it was consistent or inconsistent, and how many solutions each one is an example of. Now, Unit 1 test is a take-at-home test, so you're not having to create a study sheet for this because you're able to use your notes and your textbook. But even for a take-at-home test, I would kind of like to have a condensed set of notes so that I wouldn't have to look so much around. So even though it's a take-at-home test, it's probably a good idea to have a condensed one-sheet note just as a fast just as an easy thing to look at, so you don't have to like search through a textbook. So that's 9.2, is just identifying this, and then they go into some more application questions. But I thought that for our next Skype, which is next Monday, that I could go into some of those longer word problems, application questions, and tackle the discussion question for Unit 1 as well. So I think I might wait and do those harder questions next week once people have had practice with creating these matrices. How does this sound? Does this kind of bring you back to linear equations and the idea of consistent versus inconsistent systems? Are you able to see that connection between the linear equations and now these equations in 3 variables?
Yeah, I can see it. Like your non-square system there, that obviously represents the third illustration with everything being flat on top
Yes.
of each other, right? So
Yes.
there's no z dimension, so to speak.
Yeah, exactly. You got it. Very good. And
Yeah,
then they'll
well,
go.
I got the concept, but we'll see how the
Yes.
math goes.
And then we can bring that back on Monday too when you start doing the practice around that, because what you'll find that will happen is, oh, this is so super small. And I don't know if there's a way to bring it bigger, but this is showing a non-square system. So it's 2 rows instead of 3, right? So here's the equation. Whoop. Here's the 2 equations in 3 variables. And so what they do is they put that in a matrix, and they can only have 2 rows. And then what they do is they take that matrix with the coefficients and they put it into this row echelon form. So they try and get the ones in the diagonal and the 0 underneath as close as they can get. What this means is that because you don't have the last row, then Z is going to be any real number. That's what that means, that Z is going to be any real number you put into it. And then I'm going to grab my pen. So looking at row 1 here, it's going to be x plus 2y plus z equals 8. And the second row tells us that we have 0x because there's a 0 in the first one, so we don't add that. But we have y plus 3z is equal to 2. And then what we can do is solve for y with this equation. So y is equal to 2 minus 3z, where z is any real number. Oh, I can't put a z in there. Oh, the limitations of Skype. Here, I'll move that. So y is equal to 2 minus 3z. I'm going to get rid of that there. So far we have z is any real number. And then we have y is equal to 2 minus 3z. And then we can put 2 minus 3z in for y here and then solve for x. And they find that x is, they did that right here. Sorry, this is really small. Um, but they did that here and then combined like terms, and they found that x was equal to 5z plus 4. So 5z plus 4. And that's going to be your solution. So as long as each of the values of x, y, and z are represented in one variable, in this case it's z, then you have a solution for infinite many solutions. And how you would work this is then whatever you give z as, so let's say z is equal to 50, you can then input 50 in for z for all the values and then figure out what the x and the y value will be. So that's just a little precursor, a little taste of what's to come in 9.2 with the non-squares, but that's kind of the solution you're looking at, is that your solution won't be all constants. It will just be in terms of one of the variables. So in this case it was in terms of z, where z was any real number. But you'll get to that. That's kind of the end of 9.2, and I would expect that this would come around Sunday. Thanks for coming back, TJ. It was nice to see you in class tonight, and maybe we'll get to see you on Monday as well. I'm sure you'll have more questions. If you can't make Monday night, then just email me, okay? Sounds good. See you later. So Andrew, did you want to, did you have any questions you want me to put up, or did you want to work on something for the last like 15 minutes and then come back in and ask me questions? It's really up to you how you want to use the last part of this tutorial. Oh, and we have another person, Matthew. Matthew, if you can hear me, let me know. And Andrew, if you have a question, let me know.
I think I'm good. I'm gonna, like I was, I'm just gonna go back to the video that was posted earlier, and I was going through it and writing down the steps and stuff. So
Perfect.
I'm gonna go back to that, and then I'm gonna try to get into MyMathLab and see where it takes me.
Great. No, that sounds like a great strategy. And if you run into difficulties, just let me know. You can hit that instructor help button in MyMathLab, or post to the Q&A, or send me a question that way. And I'll be back here on Monday night too.
Okay, thanks a lot. We'll see you then.
Great. See you later, Andrew.
Bye-bye.
Hey, Matthew. I didn't see you come in. Did you just arrive?
No, I came maybe about a half hour ago or so.
Oh my gosh! Yeah, I am so sorry. It's this Skype. My participant list wasn't down far enough, so you were hiding under TJ. I'm so sorry. How are you?
I'm not too bad, thanks.
Good.
I just noticed what time it was at, and I showed up maybe like 15 minutes late or so, so I just wanted to see what was going on.
Oh yeah, no, that's fine. So so the Skype session that I have is going to be once a week, and I've planned them for every Monday so that we're consistent. They're not mandatory; they're just here for extra help, and
Yep.
and you can come in anytime, so you don't feel like you have to come at the start and stay for the whole thing. You can pop in and out. That works too, and it's more of a tutorial. So students kind of watch the review movies if they can, the videos, and then you can bring your questions, and then we can go over them here, or you can just see what everybody else is asking, and just listen if you want. It's totally up to you.
Okay, no, that's great. Yeah, I did some of the starter stuff today, and then I was just kind of looking at what you were doing with the matrices and everything. So I think I have a pretty good understanding of it, and I have some friends that are math majors that I'm asking for help on stuff that I don't understand too. So it's working out pretty well so far.
It takes a village, math.
Yeah, pretty
Yeah.
much.
No, that's great. That's a great strategy. And if you have buddies that you can help if you have questions, that's great. And I'm here as well. I know that my students who were with me in 1046, they use the instructor, ask my instructor in MyMathLab if they had a question. So feel free to use that, and you can also use the Q&A, and you can also email me, and we have Skype as well. So definitely like send me your questions when you get stuck, and I can quickly run off a solution to you or a video. That's no problem.
Okay, that's great.
Great. So did you have any questions you wanted me to go over that you're stuck on? I know it's only day 3, so I'm not expecting a whole lot, but if there's anything you want me to go over.
Nothing that I can think of right now. I think
Okay.
I haven't touched too much stuff, but just from everything I've seen so far, I think I'm doing okay so far.
Okay, perfect. So if you want, you can, I'm going to stay here until 8:30, so another like 12 minutes. I'm going to process the recording that we have, so I have to stay for that. So if you wanted to work on something and then come back in and ask me a question, I'll be around for the next 15, 20 minutes at least.
Yeah, okay, great.
Okay, sounds good.
Thanks very much.
No problem.
Bye.
Bye.